Thanks to Geology for sponsoring today's video. I think most of us know what the planets look like in the visible light spectrum. Saturn's pale golden colour, Jupiter's red bands and colourful clouds, and Neptune's dark blue hue. However, light is emitted or reflected by planets in wavelengths beyond our eye's capabilities, like infrareds and ultraviolets, and often what we can see in these wavelengths is actually far more valuable to scientists than simply how a planet would appear to the natural eye. That's because certain things that are invisible to our eyes might be very visible in infrared or ultraviolet, or vice versa. And if we want to know what substances are found on a planet, the electromagnetic spectrum can help us again. I'm Alex McColgan and you're watching Astrum, and in this video I want to focus on what we've seen through more of the electromagnetic spectrum on Jupiter and some of its moons, and how this different approach may give you a new perspective on the largest planet in our solar system. Just as a point of comparison, let's first look at how Jupiter appears in natural light. The various spacecrafts that have passed Jupiter have revealed it to be a beautiful planet. You will immediately see a lot of the main cloud deck of Jupiter in visible light. These are not water clouds like on Earth, but rather ammonia ice clouds. If you look closely, you can start to perceive the different altitudes of these clouds. The dark, narrow regions are actually shadows cast by the tall, lighter coloured clouds. It seems like the higher in altitude these clouds are, the lighter they become, which can be seen in the highest altitude pop-up clouds in this region, which are snowy white. The process behind the different colours in Jupiter's atmosphere isn't completely understood, but it's believed to be caused by the upwelling of compounds that originated deep within Jupiter suddenly becoming exposed to the UV radiation from the Sun. As they lift up to the highest altitudes in Jupiter's atmosphere, these compounds begin to darken, eventually sinking back down again into the lower altitudes. But as you can see, Jupiter's ammonia cloud deck is opaque. We can't see through it. If visible light was the only wavelength of light we could work with, the vast majority of Jupiter would remain a complete mystery. Luckily, we also have instruments that can see beyond our eye's capabilities, and in certain wavelengths of the infrared, we can see Jupiter in a completely new light. Perhaps the most striking is to observe Jupiter using the 4.68 micron wavelength, as this shows the heat of the planet. Very interestingly, in this view taken by the Gemini Observatory, it is the lower altitude reddish bands that are the brightest. You see, Jupiter actually emits more heat than it receives from the Sun. It is contracting in size, which heats it up. This heat eventually makes its way out of the planet through the cloud deck. The heat escapes easiest where the cloud deck is thinnest, which is why features like the great red spot and the white bands in visible light are dark in this image. Luckily, we aren't just limited to a disk view of Jupiter either, thanks to the Juno spacecraft that is in orbit around Jupiter right now. Viewing Jupiter's poles in infrared again, scientists were able to create a 3D map of the incredible vortices that are found there. Jupiter's North Pole has 9 seemingly constant vortices, 8 in a square shape revolving around a large one found right in the center. Again, you'll notice that it is the lowest altitude regions that are emitting the most heat. Because this wavelength only reveals heat, the haze and shadows in the atmosphere don't block the view as much as you would get in visible light, meaning it can give us an unprecedented view of the 3D structure of these vortices. It's still pretty cool here for Earth standards. Even the yellow sections are only -13 degrees Celsius, with the darker, higher altitude regions being -83 degrees Celsius. And because the heat is coming from Jupiter itself, this view is available to Juno night or day. It isn't reliant on sunlight. Storms can show up in infrared before they are noticed in visible light too. Look at this comparison taken by Hubble. These near-Earth-sized storms located beneath the cloud tops are much warmer than the ambient surroundings, indicating that internal heat does play a big role in generating atmospheric disturbances. And while we're on this wavelength, let's also have a quick look at Jupiter's volcano moon, Io. Unsurprisingly, Io's night side is totally lit up by the volcanic activity on its surface, making it very easy to identify new volcanoes, and to keep track of the ones we already knew about. Juno has had several looks at Io, each one revealing it to be a hive of activity, a truly hellish yet intriguing world. In fact, all of the Galilean moons have been examined in infrared, but using specific wavelengths which can reveal different things. For instance, here is the Galileo probe's infrared view of Europa in the 1.5 micron water band. When viewing an object through this particular wavelength, we can see locations where water is present. The deep blues in the image are the locations of the purest water ice, whereas other colors indicate a mixture of water ice with other minerals. This is called spectroscopy, where you can ascertain what molecules are on a planet without actually having to land there. You see, when white light reflects off a certain atom or molecule, that molecule will absorb a band of light and reflect the rest. If we analyze the missing light band, we can know what the molecule is. So think of this image less as a photo, but rather as a graph of data, indicating locations of certain molecules, colors arbitrarily chosen by a scientist to represent the data. For instance, if we look at this image showing the absorption band for sulfuric acid, it is the brighter regions this time that show where the abundance of sulfuric acid on Europa is. This abundance is found around the surface's cracks, so it may come from the ocean below the crust, but it's also found on the trailing side of Europa, seen on the top left of the image. It seems that as Europa orbits, it is bombarded by sulfur ions. Incredibly, this sulfur probably originated from the eruptions of Io's volcanoes. If we look at a crater on Callisto, infrared data has been overlaid onto a visible light image. Reds indicate more water ice, blues show less. This is pretty interesting, as this is one of the highest resolution infrared images we have of a body around Jupiter, this image only being 200 kilometers across. It adds a lot of information you wouldn't get from the visible light image, namely, there's a concentration of water in the crater, but a ring directly around it where no water is present. And then water appears again in this ray system coming away from the crater. The icier regions come from the impactor exposing the ice beneath the surface, but why there's a ring between the center crater and the debris from the ray system is a bit of a mystery. Perhaps the icy debris from the impact didn't start hitting the ground until it reached this distance out. In any case, this image shows that non-ice materials only make up a thin layer on the top of the surface of Callisto. And what does Jupiter look like through certain bands of infrared? This image is really interesting. The top left and right images are taken in 1.61 and 2.73 microns respectively. In these bands, we can see the cloud deck similarly to what we can see in visible light. However, in the middle, we are looking only through 2.17 microns, the absorption band of hydrogen. As we know, Jupiter is predominantly hydrogen, meaning the hydrogen in the atmosphere suddenly becomes opaque and visible in this wavelength. In fact, the only features still visible are the really high altitude clouds, the ones that poke through most of the hydrogen in the atmosphere. The bottom left image is the 3.01 micron band, where there is some absorption, but not as much. At this band, it is methane and ammonia that are absorbing the light. Bottom middle is at 4.99 microns, giving us another heat map, and bottom right is a false color combination of all 5 images, which is what you see happening if ever I show a false color image in one of my videos. Now you know what these false color images are trying to show. The last interesting view of Jupiter I want to show is in the ultraviolet. Absorption spectroscopy in the ultraviolet isn't super useful in planetary astronomy. The only time I can think of it being actively used on Jupiter was to track the impact of comet Shoemaker-Levy 9 back in 1994. There, the dust absorbed a lot of the UV sunlight, and so scientists could easily track winds in the planet's stratosphere by watching the evolution of these features. However, molecules that are hot enough will emit light in lots of different wavelengths. And there is a bright source of light coming from Jupiter in ultraviolet and infrared. It's auroras. Jupiter's auroras are extremely powerful compared to the ones on Earth and are a permanent feature on the planet. Hubble, which can see in ultraviolet, has been tracking Jupiter's auroras for years, although the best views have come from Juno in the infrared, simply due to Juno's orbit taking it over the planet's poles, whereas Hubble's viewing angle makes observations difficult. These auroras are strongly influenced by the magnetic field environment of Jupiter streaming particles into its upper atmosphere, plus from the flux tubes between it and its moons. So there we have it, a look at Jupiter in a very different way than what you may be used to. And as you can see, absorptions and fluorescence through spectroscopy can help us understand a planet far more than what only visible light can reveal. We can determine molecules and minerals, observe a planet's heat map, and view aurora interacting with the planet's magnetosphere. Everything together helps us get a more complete picture of how a planet works and why it behaves the way it does. Want more videos about this for the other planets? Let me know in the comments below. Thanks again to Geology for sponsoring today's video. Now, years of planning goes into the picking and building the very best instruments to take on space probes, and the same has been done with picking the very best ingredients for skincare, because skincare is also a science. Geology are proud of its short list of proven ingredients like salicylic acid and retinol, and through their purchasing process they will tailor the formula just for your skin type. Knowing that gave me a lot more confidence to use their product myself. So if you are tired of acne, wrinkles or other blemishes, I suggest you give this a go. Using my link below, you can get 50% off a 30-day trial set, so you can see for yourself if it works for you. If you want to continue, you can subscribe to save or go a la carte. It's up to you. Thanks for watching. If you want to know more about Jupiter and its moons, check out the playlist here or click on the cards icon in the top right. I hope I earned your like and subscription today, and a big thanks to my patrons and members for supporting the channel. If you want to support too and have your name added to this list, check the links in the description. All the best and see you next time.